So for vectors, we need to have indexes to be able to retrieve the data that we want in a reasonable time frame. And because of the type and nature of vectors and doing similarity search, it can be quite a long time to be able to complete, because you're effectively doing an n by n kind of set of calculations. And although the math behind a lot of these calculations is relatively straightforward, it's still a reasonable amount of math that needs to be done in order to be able to be completed. So doing this on the fly or on an ad hoc basis can take a bit of time. Okay. Now, we know databases, or traditional databases, if you want to call it, our multi-model modern databases, are really good at doing the kind of very simple, straightforward pattern matching indexes. And as we've discovered, or as you would discover if you looked into the different types of indexing approaches that they have in the more recent times, is that there's a lot more kind of more complex searching, indexing, and search patterns within those databases. Now, some of the approaches that we can use for vector databases and vector searches are actually kind of already within some of the databases, and what we can do then is just look at, well, what are these kind of capabilities that are there. So if a database, an enterprise modern database, doesn't have it now, well, it probably has it this year, or kind of been included this year, but they're going to be added really soon, and we're going to see more efficiencies being driven into making the performance of these a lot more responsive to us. Okay, so why do we use indexes? Well, we want to be able to reduce the search space very, very quickly. We don't have to search through every single record and every single vector and all the dimensions that might be in vectors on it. We want to reduce down the search space really quickly, and that's why most enterprise databases can easily scan many hundreds of millions of records in a fraction of a second or in a couple of seconds. It's really simple to do. You don't need big data platforms and NoSQL databases to be able to do all of this. So building upon the amount of programming and the fine tuning and performance enhancements that have gone into enterprise databases, particularly over the last 10 years, we can build upon that work to be able to use as part of our vector searches. So as there's a kind of well-known kind of person on NoSQL, Marcus was it, who has now used the index Luke, we need to use indexes. Right, we can't get past it. If you're not using indexes on your data in your normal enterprise databases, they're going to perform slow, and particularly as data kind of increases. But when we start looking at this, is that an index is going to consist of some of the details of the embedding. It's going to have things to do with the distance metric. So some of the distance is already calculated, and it's also going to have what's known as a row ID or a record level indicator of where can I go and get it from the file system. So being able to get fast retrieval from all of those. Now, when we look at all the different types of indexing that's available, when it comes to vectors, they can be kind of grouped into kind of four main types. One is hash based, the second one is tree based, the next one is graph based, and inverted file based indexes. Now, when we look at all of these, is that we do need to be a little bit kind of careful sometimes of it. If we have endless amounts of disk space, then fine, that's great. But if we want to load these into memory, which is where we're really going to get fast responses, is that given the number of dimensions that we have, is going to take up quite a bit of memory. Now, in most kind of, say, set up and play kind of environment. So in some of the examples I'll give, using an Oracle database, I'm just going to set the memory requirements quite small and just work with kind of data that can fit within that. But within your production environment, we are going to need a lot more memory allocated to storing these indexes. And in most production systems or kind of mid-level servers, we can have hundreds of gigabytes or even terabytes of RAM, which is not necessarily much of a challenge for us, but a lot of that is actually quite cheap to add to our kind of server environments. So if we look at the first one that we have, which is to do with hash-based indexing, and this is just your ordinary normal level hashing indexing. Right, so we have an algorithm which is kind of specifically tuned for working with kind of vector data. We pass it through that hashing algorithm, and it ends up by identifying what kind of bucket, or what kind of, we divide it into a number of buckets or areas, and being able to hash the vector, and vectors with similar kind of values will end up by going into the same bucket. So that means when we come to search, we just go and look in that bucket to be able to kind of get the data out. So it's really quick and really efficient at doing it, but there is some limitations about looking at the accuracy of it. So you are only looking in that bucket, you're not necessarily looking outside of that bucket, which might actually give you better results on it. So there's a certain kind of, just fast, but it's also kind of, accuracy on results. Now, with all of these different indexing techniques, there is a bit of an issue about, when we have new data added in, is that, if we're constantly adding new data in, the rebuilding of the index may not actually work quite well. Now, with the hashing, it's not too bad, right? Which kind of allows us to be able to use this in those scenarios. The next based approach is to do with a tree-based indexing, and this is quite a fast approach for doing searching, because if we do the your typical, if you want to call it binary tree, or your typical decision trees type scenario, you end up going down certain branches, so you get to the data points you're looking for quite quickly with the minimum number of steps to be able to perform. So it uses this approximate nearest neighbor to be able to search down through the different branches to be able to find the one that we want to be able to do. But just with like any sort of tree type environment, as we add more data in, is that sometimes we can end up by having the tree become an imbalance, or we might need to rebuild the index at some point, because it becomes not as maybe accurate as it should do. And if you want to rebuild the index, that can take a little bit of time to do. All right, and sometimes what you end up by having to do is just a rebuild, which kind of rebuilds it from scratch in order to build it out. But if your data moves slowly, or kind of it's not necessarily too much of a big deal, and you can set the rebuild to be done at kind of quiet times within your database. One of the more popular approaches is to do kind of graph-based searching. So it's kind of similar to tree-based indexing, but with graph-based indexing, it looks like kind of grouping kind of similar data points by connecting them using edges. So graphs and edges, which is common within this. So with the graph-based indexing, it's useful when we want to look for when we have really high dimensional space. So this is where we go from the vector embedding models from over the last few years into more kind of ones we have had in the last year or two, where we've gone from a few hundred dimensions into thousands of dimensions. So this can work quite well within that, and it ended up by creating different layers of search space. And as we kind of go through, look at an entry point, we find what the appropriate next nodes are, we find the layer for that, and from that we can go down through the layers on it. So you might kind of think this is kind of similar within tree-based, but it's a different way of laying out the data. So it's a really efficient way of being able to search through the data and reduce down the number of data points that you need to look at quite efficiently. But again, we have the challenge of, as we add more and more data into our data set, is that at some point we need to recreate this, and this might need to be recreated a little bit more frequently than maybe the tree-based kind of approach. The inverted file is just kind of this, if you've kind of done stuff on text mining and stuff like that, you will have kind of come across this. So with the inverted file, it narrows the space by partitioning the data set into different kind of, if you want to call it, clusters, because it uses k-means to be able to divide out the data, find data that's kind of more relevant or related to one another than others. And then when you go searching for the data, is that you just look in the particular cluster for the data that you're actually looking for. Now, there can be some data accuracy issues in relation to this, but because maybe a data point across into the next cluster is also kind of relevant. But we can do that. Now, as we add more and more data, this might slightly distort the clusters, right? Which means we have to kind of rerun the k-means algorithm, which is actually really efficient at doing this, even on pretty large volumes of data. Now, given the degree of dimensions that we might have, it could take a few minutes to run on a relatively large kind of data set. So that's the inverted file. Now, And there's different variations of to do with the hierarchical navigable small world, using the locality sensitive hashing, and then we also have product quantization, like as another kind of more memory resident efficient kind of approaches. But those two ones, the hierarchical navigable small world and the locality sensitive ones, is the ones, they're the kind of main algorithms, and other ones and are built around those to give variations of it. Now, when it comes to kind of maintenance of these indexes, it can become a kind of a complex kind of process. Well, it depends on your definition of complexity. Is there a bit of work involved in doing it by the computer, not necessarily by you? Yes, there is, but what you need to do is look at the overhead of doing it and when might be the most optimal time of doing it, because a lot of these indexes do need to be rebuilt as we're adding more data in, or data gets updated. Now, given the nature of a lot of this data, it doesn't necessarily get updated or changed. We just get more data added in. So one of the things you can do that offline, bring it in. You can do an offline build of the index and then enable it and replace the existing ones. So there's lots of things to be able to kind of consider, and that's something that you need to discuss with your DBA. Now, when we start looking at all of this, is that, if we take the Oracle database as an example, and other databases are kind of similar, is that, we can do vector searches in there. And within the database, within the 23 AI database, we have two particular types of indexes. One is kind of, disk based, and the other one is to do with being memory based. So we have different structures and being able to partition it based on that. So the kind of the in-memory one is based on our graph vector index. So kind of what I've described previously, that's kind of how it works, and being able to do that in memory makes it really, really quick, really, really efficient, and almost like real-time responses on what we're actually trying to search for. And then the more kind of disk-based one is to do with the inverted file kind of format, using the k-means kind of algorithms. And we get to see here as an example of how you can actually create a vector index. So say we define create vector index, we give it a name, we tell the table that it's going to be on, we give the column name, and then we can say what type of organization that we want. In this particular case, we can say is the kind of neighbor, which is going to be the inverted file kind of format. We can say what the default distance measure is going to be, and we can add in other criteria to do with accuracy, how close or not they are, which is can be additional measure that we have stored within those.